So Professor Dimos Poulikakos holds the chair of thermodynamics at ETH Zurich, where in 1996 he founded the Laboratory of Thermodynamics in Emerging Technologies. He received the White House by NSF Presidential Young Investigator Award in 1985 and the Reviewer of the Year Award for the ASME Journal of Heat Transfer in 1995. He is the 2012 recipient of the Max Jacob Award for Eminent Scholarly Achievement and the Distinguished Leadership in the field of fluidics and heat transfer. His research is in the area of interfacial transport phenomena and thermodynamics and on the development of energy technologies. The focus is on understanding the related physics, in particular at the micro and nano scales, and employing this knowledge to the development of novel technologies. He is the editor-in-chief of the Journal of Experimental Heat Transfer and a fellow of the American Society of Mechanical Engineering. He represents Switzerland in the World Assembly of Heat Transfer Conferences.
So over to you, Professor.
Yes, thank you very much for the introduction. Let me apologize for the mix-up that I caused yesterday. I think we exchanged a little bit with a major organizer of the conference, and I don't want to go into the details, but I'm happy that we can repair some of this by me being able to give the talk today. And I chose a sort of a different topic, perhaps. I didn't have the chance to attend the conference so far, but a topic that perhaps is a bit different than the pure thermal management aspect of computer electronics and all kinds of electronics. And I'm going to talk about high-performance computing and cooling of high-performance computing, and not only cooling, but powering of high-performance computing, which today is done, of course, by just plugging in the computer into an electricity network, and discuss sort of the option of doing things very differently than what we've done before. At least starting to think in that direction. Okay, so then I'm going to start by let's see. Okay, very good. We'll provide you a bit of a background on information technology and energy. So the information technology, although it's not as obvious as the airline industry, is responsible for a large portion of carbon dioxide emissions worldwide, and it basically consumes quite a bit of primary world energy. And if you count everything together, the information technology sort of industry is not that far from the airline industry. Okay, that gets a lot of bad press. Well, for us, the information technology industry does not get as much bad press, so to speak. And new data centers for petaflop computers, for example, they need something like 10 megawatts of electrical power, and this power fully is converted into heat. And with traditional technologies in the large data center, this heat is low-grade heat, and it is basically wasted without reuse. Okay, so and of course, with exaflop computing coming in line into the future, it will be very difficult to basically cover energy costs. So at the same time, a data center of not a very big one, 10 megawatt data center, if it is converted so that we can use some of this heat, basically we could easily save a large part of its energy and use it for example, for heating of industry needs, or industry needs in heat, or simply heating homes in the neighborhood. And that gave the initial idea of some work in developing what was called a few years back the green data centers. And that is where we were active for the past, 15 years or so, together with IBM, having the vision of creating a zero, so to speak, emission, near zero emission data center by incorporating liquid cooling in the function of the data center. Let us take a look at the typical data center cooling process. So you have the electronics here, usually in racks in these closets, and these closets come with fans, okay, and the fans blow air effectively on the electronics. The air becomes hot, okay, and this air usually is then eventually dissipated in the atmosphere, and the potential of using its energy is effectively dissipated and lost in the atmosphere. So effectively, the cooling aspect of data center with this principle is effectively it's a nightmare, because you do use the electricity, you waste all the heat that comes from the you use electricity for computing, of course, and then of course the equivalent heat, low-grade heat, you completely wasted in the atmosphere. Plus, you need, of course, air conditioning in the room. So effectively, you use additional electricity, of course, to keep the temperature down. So it is extremely inefficient from the energetic and exegetic, of course, standpoint. Right? So we worked with IBM and had the idea of doing things differently, in that using liquids to cool the computer. Of course, with a liquid, the cooling capacity will be much higher, because many liquids carry a lot more, they have much higher heat capacity than the air. The related flow rates, of course, if you use liquid coolants, will be much lower. And the question is what liquid? And the first thought was to use liquid dielectric liquids, but those have a tendency of boiling at temperatures that are that are reached by chips during their operation. And if you're boiling, you have all kinds of instabilities. And while for some applications that is doable, for many other applications, it is not doable, right? So after a lot of discussions, we were forced to use water. So effectively, we decided to cool electronics with water. And the principle is shown here, where effectively you use water to do the cooling of the computers, the how we'll discuss a little later, and then you take the warm water out of there with a temperature of 75 degrees. We can go up to 85, 90 degrees, because the chips get quite hot. And with some kind of heat exchanger sort of arrangement, you can use it you can use it in the industry, or to basically provide thermal energy to homes and so on and so forth. So for district heating, in other words. So the entire scientific game then became, how do you do this, having water, and then bringing the water as close as possible to the heat generating chips, all right, because that's the heat is generated, and then removing the heat from there at a high temperature. So effectively, you have high value heat, which you could later reuse. And that is where we worked into this sort of micro heat sink design. We use some sort of bio-inspired principles, and we are able to design and make systems of this kind that actually work. And you can see them here, where you see chip arrangements on a board, and on top of this you see this micro-scale bio-inspired heat sinks, which I have no time to discuss with you in detail today, but of course we published a lot in this area, so you can find out if you're interested in. Then all that, and I want to basically then stress here, when you do research in this particular area, it's also very constructive. You work with the industry. We put together the devices. We built the supercomputer. No, we didn't. I use the word we, but actually IBM then built the supercomputers. And you can see this new generation of supercomputers here, two phases with, so of course, they are liquid water cooled, so to speak, and the waste heat is being fully used. And the first of this kind was used, it's called SuperMOOC, and it's used at the Leibniz Computer Center in Germany. So with that, we felt good, and we sort of closed this chapter of the work. Again, if you're interested to see some of the history, you can go back to some of our publications and check it out. But this supercomputer, at its time, because time runs very fast in computer lives, all right, was the most powerful and energy efficient computer in the world at about 2015, 16 or so. Now, after that, of course, we thought further and tried to look further into the future and think about energy efficiency versus size, packaging, and powering sort of all together. And what drove us to that was some facts of life, all right? So if you look at how much $1,000, how much computational power $1,000 can buy, okay? So $1,000 could buy, in terms of computations per seconds, in 1960s, you know, or 60s, let's say, 60s, 70s, so about 1 million computations per second. Okay? In 2020, it could buy 1 trillion computations per second. Okay? So things improve exponentially. So then the technologies, that drove the technologies to grow in terms of device performance dominating, device-centric performance, all right? Okay. At the same time, if you think a little bit deeper, how computers work, where we want to go into the future, because we do get this performance but consume a lot of energy, you have to start thinking about efficiency. Okay? So then here on the right-hand side, I'm showing you a density-centric viewpoint, all right? And this is looking at your computational efficiency, which is operations per joule spent, okay? Operations per joule. And then you see here the computers, all kinds of computers going from earlier all the way to, I don't know, in the mid 2010s, 2015. And what you see up here is basically estimates of brains. And you see the human brain is not that much different than that of a mouse, really. So that should make us worry a little bit, or of a monkey, or of a whale in terms of computational efficiency. But if you compare here computational efficiency, which is important if energy is important to us, and it is very important, all right, or saving energy, and you look at the numbers between here, which is sort of close to the highest efficiencies machines have, and here, what simple brains have, you see that the brain is about 10,000 times more efficient and denser than the state-of-the-art computers. Okay? And the reason for that is the structure of the brain and the fact that communication of the different parts of the operation of the brain are done over very short distances. Okay, so an important problem is that memory proximity is lost in current computers, and that is detrimental for efficiency. So the idea out of some thoughts and discussions like that came to redesign the entire sort of thinking of computers in terms of improving efficiency and take a density-centric viewpoint where we care about operations per joule, okay, and not simply number of operations per second. Okay? So, and with that argument, of course, I can rephrase it by saying that size matters very much in computers. Okay? Keep in mind that transistors, if you look at the supercomputers of today, transistors occupy 1 part per million of the system. It's incredible, actually. You see, where basically the computation of the operations are an extremely negligible small part of the system. Never before devices like transistors occupied a smaller volume fraction of the computer. If you look at the energy of the how the energy in a supercomputer is expended, you will find out that most of it, an overwhelming part of that, 99%, is spent for communication, and only 1% for computation. This is actually amazing. Because most of the energy, or the lion's share of the energy, is spent is shifting the information around in the various parts of the computer and the logic, and only a very small percent for computation. So, and of course there is reasons for that, and gradually we reach the point, if we put them together sort of conventionally, that it is impossible, and we tried this, to basically power and cool computers separately, so to speak. So that is having a cooling system of the kind perhaps that you're discussing in this meeting up to now, and also power the computer at this very high densities we want to achieve, it is impossible. So effectively, the approach we took is an experimental approach, and of course has not reached the final goal yet, is to rethink the entire story and try to fusion the powering aspect of the computer to the cooling aspect of the computer. In other words, the liquids that do the cooling, which in our state of the art up to now, as you saw earlier in the first slide, few slides of my presentation, were water. Instead of using water, we should use liquids that also, through chemistry, provide, so to speak, electric power. That is, they generate electrons, so we can drive the computers through those liquids. So you see an example of a device here, but we then proposed a paradigm shift, going from two separate systems, going to an on-chip power generation. That is through chemistry, in a similar manner as blood. Okay, we will have a cooling aspect as well as a power generation aspect. Okay, and then for the power generation part of this, we use the principle of a redox flow battery. So by designing in terms of doing the cooling and electricity delivery with flow batteries, we combine then the two together, and effectively chemistry will do the powering and not electricity from your power plant, so to speak. I have no time, unfortunately, to discuss principles of flow batteries. They exist, we didn't invent them, obviously, but you see here that they're large devices. Okay, so effectively, the state of the art of flow batteries, as we started this research, is of the kind that you see here. You see human-sized installations and so on and so forth. The principle of the flow battery, I'm trying to show them in two clicks here, and show you it's not different than one of a fuel cell. You have an anode and a cathode, and during the charging time, you charge your chemicals. Discharging time, you generate electricity. But again, you know, they're designed for large-scale installations. And in our case, we want to miniaturization is a challenge. And of course, we have, compared to the existing state of the art, a power density mismatch for these large-scale redox flow batteries. And that is actually one of the disadvantages of the technology. The power density is rather small, 0.1 watts per square centimeters. And for what we needed about 10 watts per square centimeters for powering the supercomputer. So we're basically, we had the idea, it sounded very exciting, but then we did have this barrier to overcome, where we had to go up by 2 orders of magnitude in power density with respect to the state of the art. We knew that this is a huge obstacle. We knew that it wasn't necessarily very probable, although possible, not very probable, we would meet it within our means at that point, but we tried to do the best we could. So effectively, that is the premise, all right? So we try to use flow batteries to provide both cooling and electricity in the supercomputers. And now when you talk about flow batteries, the problem goes down then immediately to thermochemofluidics, all right? And effectively you have arrangements where classically you have membrane-based flow batteries, who are effectively have anode cathode separated by a membrane, very similar to a fuel cell, all right? Is of the same family device, all right? And then the whole story is how do you arrange the microfluidics there if you have small-scale devices. Or you can try to go without a membrane, where effectively you could have an oxygen and a fuel flowing in parallel it is a lower laminar flow, no Reynolds number laminar flow, and then you basically do your chemistry through these streams flowing parallel to each other. Do not mix, because if you mix, you lose everything, of course, right? Because you want to have the chemical reaction taking place at the interface without intermixing. If intermixing takes place, you basically mix your reactant with your oxidant, and then the entire process ceases to exist. Okay, so clearly you have more potential here, but also more complexity. Less potential here, but interest in thermofluidics, perhaps, and less complexity. So we spend a little bit of time, although we didn't have very high hopes, looking at some scientific aspects of the membraneless fuel cell. I'm not going to show you the results, but a bit the principle, tell you what we did. So effectively, you have the cathode light and anode light that will fly in parallel here, all right? And then on the top and the bottom of this channel, you would have the electrodes collecting the current, right? And those would flow in this direction. One side with the cathode light, the other the anode light, and the reactions would take place at the interface without mixing, because the Reynolds number would be small. You could start getting more complicated, as we did, of course, because the first simple solution did not work, did not deliver the power density we wanted, by intensifying, of course, the process without causing mixing. So effectively, imagine that if you put structures at the bottom of this sort of channel, and this is a typical herringbone structure, one stream will come in this direction and start rotating. The other stream will come in the other direction and also start rotating, but each one will stay at their half of the channel. Because if they cross over to the other side, then of course you have mixing across the two different liquids, cathode light and anode light, and then of course you destroy the process. So we do sort of view them rotating, co-rotating like that. And by this co-rotation would of course enhance the chemical reaction at the interface. And we try to see how far this would go. And we tried, of course, several arrangements with these symmetric flow promoters, as you can see here. Empty channel, simple herringbone with a structure. So here you allow the rotation here and there, but you have a little separation zone to sort of help in blocking the mixing. And then, of course, you don't have anything with S4, okay, in the middle. It turned out, I'm going to make a long story short, that we never managed to go not even up to an order of magnitude. We need 2 orders of magnitude. We did a little better, but we didn't do than the large scale sort of systems. Well, I mean, not even to be frank. Now I remember, but you know, the performance was low, but we did have a lot of fun, sort of investigating the fundamentals of this sort of microfluidics process involved, and the involved mass transfer and heat transfer. So it looked to us that that this is not the way to go. Of course, the other aspect is what kind of electrolytes you use, and then there is a different story, okay, of selecting appropriate electrolytes and so on and so forth. But from the thermofluidics, from the fluidics viewpoint and the vortex generation that I mentioned before, it's all the same. And decided then, of course, after a while and after having our fun, to sort of let this go. Okay, although if you have a technology where you do not have this higher power densities that we need in the high performance computers, this would be a viable solution, right? But for our technology, it was not. And we decided we need to go with membrane-based devices and then deal with the necessary accompanying complexity of this process. And then, of course, the challenge was here to do the microfluidics, okay, and related heat and mass transfer. And I show this here, pardon my German, as they say, in terms of the cartoon. All right, you still have anode, cathode, and the membrane in the middle, and then you design this sort of channel, interdigitized channel systems that will do the fluidics and some of the stuff that I told you before. And think about then that something like this would be then removing the heat from from a system of one electronics sort of a board or a system of chips that you have at the bottom of this, at the top of this, and so on and so forth. So, and the challenge was how you do this, and I'm going to try to show this in detail in this place. So we're focusing here in the middle of the system, and then you have the anode, the cathode, and membrane, and I'm trying to show you a cartoon of how the system would work. So you have the analyte and the catalyte with the different colors. They would travel along a channel, okay? And as I'm showing in the detail here, they will be pushed down, both the anode and the cathode porous materials. They will be pushed down and then travel left and right and are collected on the channels to the left and the right. So effectively, this will be collected into that channel, and that channel, or this goes here and that goes there, and so on and so forth. So with that, you achieve a rather strong flow, and you can drive a reasonably active chemical reaction to generate the currents you want. The story is a bit more complicated because these are parallel channels, but as you see, if you travel along a channel like this and you keep losing fluid at the bottom, the flow rate decreases. So to optimize performance, of course, we were able to design and optimize this rather complicated taper channels based on calculating the flow rate that you lose in downward through the screen here, and came up with optimal arrangements that look not like this, but like this. And then, of course, you can basically make several passes. You can have systems like this and system like this. So effectively, this will be a first pass, second pass, four-pass system. And we're able to fabricate all this by 3D printing techniques that worked actually pretty well. And you can see here examples of a straight channel, taper channels, dual pass, quadruple pass, and so on and so forth. So, you know, increase in efficiency. We ran the entire thing with heat transfer, and we were able to calculate the power density versus volume flow rate. And you can see that if you look at all this, the four-pass taper channel does the best. Actually, for higher flow rates, it reaches something like 1,400 milliwatts per square centimeter, which is pretty high. It's basically pretty much the same with what we expect from the large-scale systems. But of course, you should not forget that the fact that, of course, you have to power those liquids through the channels, and for that you spend energy. All right. So if you subtract the pumping losses in a system like that, you know, which of course we have to subtract from the produced electricity to have a net power density, you see that they for very low flow rates, if I look at the quadruple pass, is doing okay. But as you increase the flow rate, because of losses, of course, a lot more complex fluidics, as you saw from the arrangement that I showed before, this is losing, and a compromise is the second pass. The second pass, the double pass, dual pass channel, does better than the single pass, but then of course also better than 3 and 4 because its losses are reasonable. So the winner here is the dual pass taper channel, okay, that delivers approximately 1 watt per square centimeter, which is an order of magnitude less than our goal, but it could be very reasonable for other applications because our demands for the cooling of electronics in supercomputers are pretty high. And that is pretty much the best we could do. If you look at United Technologies that have this large-scale channels, all right, in our miniaturized cell, without subtracting pumping losses, we're pretty much the same. But again, you know, if we subtract pumping losses, and we have to subtract pumping losses, and they also here do not subtract pumping losses, by the way, but we're about an order of magnitude below what we set out to reach. And there is a room for improvement. All you need to do, go an order of magnitude above what we've done, okay? And for that, of course, there's a lot to be done. You can work further with the fluid networks, you can work further with the chemistry, and so on and so forth. But at this point, what I showed you is what we have. And with that, I'm going to conclude my talk. And thank you for your attention, and the floor is open to questions.
Professor Poulikakos, we'll open the floor to discussion. Any questions from the audience?
Hi, Dimos. Marco speaking. I don't see you, though. We lost you.
I see you in a small box, and I hear you.
Yeah, now I see you. You disappear from our side.
Let me put it. Is that better now?
Yeah. It's good.
Right.
You didn't mention about any kind of numerical simulations of these devices. So, did you try to do numerical simulations of to optimize, for example, the geometry of micro mixings and so on?
Yeah. In these papers we've done for the fluidics, because you're in laminar flows, you can basically we do quite a bit with numerical simulations. We've done all that. If you look at the papers, yes, all that is done.
But then with the
there are two of course aspects of this. Obviously, we've done a lot in the membraneless sort of arrangement, and it's published in these papers. But also in the more complex cases that I showed you later on, if it is a laminar flow, the fluidics could be done with some more advanced commercial codes, and you can get a good idea on the fluidics. But what is difficult to do, because there are a lot of uncertainties, is the accompanying chemistry, you see?
Yeah.
So there, of course, you have to look at the fluidics in terms of pressure losses, but that is obviously the simple geometries have less pressure losses. But then, of course, they have the worst performance in terms of chemistry, because we want to deliver power, not simply to do heat transfer, all right? And that's where the compromise is. And there you pretty much have to work experimentally.
Okay. Can I?
And they're all laminar flows. Low Reynolds number laminar flows.
Yeah. But then I think that all the properties are changing a little bit when you have, of course, different temperature of the system, no? And so when you're thinking to these kind of systems, they are the given temperature, let's say, no, or not. So you need to stabilize the temperature or not. How is
the temperature? The temperature is not room temperature; is higher than room temperature, because the fact that you have the heat transfer, you will have a higher temperature, right? You know, and what is important, the effect of the temperature comes more into chemistry than to anything else, right? And then we can take that into account too,
okay.
And of course, the experiments you see this, okay? So clearly.
Okay. Thank you.
Hi, Dimas.
Hey, hello. Good to see you.
Yeah, good. So the thing is that, these vanadium flow batteries, the problem is you have shown, what happens in a cell, but it's always the stack. And, because there are required to be, maybe 20, 25, 30, 40 cells together to do the whole thing. So how the things change when you go from a cell to a stack?
No, I mean, it depends. First of all, I don't believe, do I have the chemicals here anywhere? Anyways, I mean, the chemicals, we moved away from, I think, from vanadium. But in general, you're correct. But here, we're talking about cooling of electrons in a computer. Let us not confuse this with these huge things that you make to generate power.
Yeah.
So our stacks are very limited, all right? So effectively, so there's not a big problem there, because you're not going to have a stack of 50 of this one next to the other. You can have a couple, but that's it, all right? So effectively, that's...
Okay. Thank you.
So, good afternoon, sir.
Yes.
Yeah, this is Sangamesh here from IIT Madras.
Yes.
Sir, just I want to know that warm water cooling for the data center, So what is the range of the warm water? It is above room temperature, but what is the range of the warm temperature?
Yes, that's a very good point. This is going to our older work right here. It really doesn't matter if the water is warm, because what you care about is the temperature difference, right? Because the heat transfer is proportional to the temperature difference, right? Actually, warm water is better than cold water because the viscosity is lower. So effectively, yes, I'm telling you, yes, we are cooling the computers with hot water. How about that? But for the computer, that's a cold water because the chip temperature is 80 degrees, and we're coming in with 50, 60 degrees. That's cold water. And it flows well because the viscosity is less than it would be if it was 20 degrees.
So it is 50, 60 sufficient, or it should be around 40, or what? Is there any range for that warm temperatures? It is fine for that.
I mean, I think it depends on you see, you can regulate this very easily based on the needs of. Can you see what I'm showing here?
Yeah. Yes.
Let's put it bigger. You can do whatever you want here, all right? So effectively, whatever you need. So if you look at, because you're coming in where you're limited perhaps is how much heat you can take out of the chips. But right now we've got chips that work stably up to the high 80 degrees. All right. So basically you can take our temperature up to, let's say, I'm going to tell you 80 degrees to be realistic, and then you can cool it as much as you want here. All right. But for these typical uses in the houses, say 40, 50 degrees. All right. And then you return with the rest.
Oh.
If you had uses here where 40 degrees would be useful for you, you could do that, no problem, right? Then you can play with the flow rate, so to get, so it's an energy balance here, but there's quite a bit of flexibility. That's not a problem.
Any other questions? So, Dimos, I just have a question about, I think one slide where you showed about the direct cooling of the chip. And rather than using a thermal interface material, heat spreader and cooling, I think this is now increasingly becoming the trend, considering that thermal interface is the bottleneck, although we are developing better cooling technologies. So what is your...
yeah, that's a general question, right?
Yeah. So I think you mentioned somewhere about the direct cooling of the chips, integrating a micro channel inside the chip and removing the heat than using a thermal.
I mean, this is a good, we consider this, all right? Consider this right here. You see this thing here, you see is a real board. It's inside these real computers. And the story is this. It depends how you do it. If you use water, all right, water, unfortunately, is a great liquid. It has a high heat capacity, but it's a conductor, right? So what do you want? Do you want to be 100% safe or more safe or more thermally efficient? And that is where the game was. In this computer that I showed you, we decided to have the heat sinks that are rather complex. Actually, now you can see it designed here, or the heat sinks. So they have a fractal structure, and they basically use an impinging sort of arrangement to remove the heat, but I'm not going to go into that. Separately, and use the thermal interface material simply not because we could not manufacture it on the chip. Actually, we did. We have, if you're interested in publications, we manufactured all that on silicon, right? And did all the work on silicon. It performs better, obviously, but IBM decided not to use them. So, do you do that for the science and the library? Yes, you do it. You fabricate them on chips, on silicon, and of course, you do not use thermal interface materials. But the industry is very conservative, okay? So they will not use them. Although they work and we prove them, and actually the work is joined with them, they decided not to use them and go with a more sort of take a step back in science and use a thermal interface material where the heat sink is now in itself hermetically sealed, all right? It does the work, but then you have less of a chance of a leak.
So there are no further questions. So with that, we thank Professor Poulikakos for a very nice talk today. And we thank you once again for agreeing to deliver your lecture in this.
Oh, my pleasure, and my friends down at Madras, of course, and from everywhere. And I apologize for yesterday, right? So because I had nothing to do. I was just somewhere outside drinking coffee. So. Okay.
And as a token of appreciation, we'll be shipping a small memento across to you as well, like what we did during the
so
previous
it's my
conference.
pleasure, and enjoy. Have a great rest of the meeting.
Yeah, and we look forward to hosting you in the future again if you wish to travel to India.
And have Marco Marengo walk around the campus a lot, so to exercise. Okay.
So thank you so much. Bye. Thanks for joining.
Bye-bye.